Good afternoon. This is our video lesson for Chapter 4 in Earth History class. So we're going to start with relative dating. What does that mean? Well, it's a type of dating that's not going to give you an actual age, okay? It's simply placing geologic events in a sequential order, as in what happened first, and then after that, and so forth, and what happened last. If all goes well this semester, and we get to stay hybrid, then you guys will do a take-home quiz involving relative dating. It's actually a lot of fun, and it's a chance to get a grade that's something other than the online homework or the exams. Absolute dating, also known as radiometric dating, this of course has to do with radioactive decay of certain isotopes, and we have several isotope pairs that are very useful in radioactive dating, and that's in Chapter 4 somewhere. Whether we have time to look at that on the PowerPoint together or not is a good question. We'll have to see what happens there. Anyway, so what do we really need to know about this? It means that these radioactive elements, like say uranium-235, uranium-238, decay at a known order, as in we have been able to measure the half-life and the decay rate in a lab. So the half-life is the amount of time it takes for half of the parent material, meaning say uranium, to decay all the way down to the final step, which in this case is lead. Once these things get to lead, then it's a stable isotope and it will not decay anymore. And what we do in the lab with our radiometric dating techniques is that we actually measure the ratio of parent to daughter material. That way we know how many half-lives it's been and what the decay rate is, and it gives us an actual age date. And yes, there's a margin of error, but it's surprisingly small. I mean, it might be on the order, you might have a sample that is dated at 537 million years, and your level of uncertainty is plus or minus 1.1 million years, which is a very small percentage of the time since that mineral formed. All right, now we are going to, and we'll be panning up and down as we go through here. We got a lot to cover. The basic geologic principles. And I believe you guys, yes, these geologic principles are basically going to help you with the homework that you will eventually do, the take-home quiz on relative dating. We'll begin with uniformitarianism, which we have spoke about before in a previous video lesson. And this simply says that the present is the key to the past. So the kind of things that we see happening on our planet today, like plate tectonics and weathering, also happened in the past, all throughout Earth's history, although sometimes the rates may have changed. Like, for example, the Earth is not as hot as it used to be, not as much internal heat, so the plates move a little bit slower. So the rate of movement, the timing for plate tectonics has slowed down a little, but it's still going on, and it has been going on as long as we have had, plates. All right, next one, superposition. Now we start new ones that you haven't seen yet. Okay. This states that in an undeformed sequence of rocks, meaning they have not been tilted or folded, they haven't been deformed, we know that the oldest rock is on the bottom and the youngest rock is on the top. Okay, how do we know that? Well, let's look down here at our drawing. I have a little note there. 1 is always the oldest, and then as you move on up higher in the numbers, you're getting to younger and younger material. So let's look at our drawing here. We have sediments on top, limestone below, sandstone below that, shale below that, and then another sandstone below that. We do not appear to have any kind of deformation in these rocks. It's pretty fair to say that the oldest thing here is the one on the bottom, the sandstone. We know the sandstone was there before the shale was deposited on top of it. So the shale is the second oldest, the sandstone's the third oldest, the limestone's the fourth oldest, and the sediments on top are indeed the youngest. So that is the principle of superposition. All right, let's move around the room. I'm a little tired because I have been moving some large rocks around. We're getting kicked out of our building this summer. It might be time to think about doing something else. Okay, original horizontality. This says that sediments and lava flows are originally deposited horizontally. This, of course, is because gravity exists on this planet. If you now see them millions of years later and they're tilted, this means that they were deformed, tilted, after the sediments were deposited and after those sediments lithified into solid rock. So we could say that if they are now tilted, they were deformed after deposition and lithification. So we see here some tilted layers going from left to right. We've got shale, limestone, sandstone, and limestone. And those things were not deposited going down a slope like that. That just doesn't happen. Gravity, physics says no. Next one is lateral continuity. No, these are not numbered. They don't need to be numbered. Lateral continuity says sediments extend laterally, meaning side to side, out in all directions, all 360 degrees, in all directions until they eventually thin to nothing, meaning they disappear. We might refer to that as pinch out, or reach the edge of their depositional basin. My favorite example here is the drawing that is to the right, down there by the chalk tray. So what do we see there? We see a drawing going from Raleigh all the way down to Wilmington, and then of course in blue there you see the ocean water where the sea level is today. We also have a little town called Castle Hayne. That's an H. I know the handwriting's terrible. Anyway, Castle Hayne is just outside of Wilmington, and then there's Rocky Point, which is a little further out on I-40 as you leave Wilmington and head to Raleigh. What I want to point out is that layer in blue that is dipping at a slight angle to the right, CHLS. That stands for the Castle Hayne limestone. Okay, so this is a sedimentary formation. It is a specific limestone that is not exactly like any other limestone, and it is naturally occurring in this area. And the age, 35 to 50 millions of years. It was during that time span that the Castle Hayne limestone was formed. Now, something I don't think I've mentioned yet is that every sedimentary rock is going to have a depositional environment. Okay, and the depositional environment for limestones is always marine, which means seawater, salt water. So looking at our drawing, by the way, we will get more into depositional environments when we do Chapter 6. Chapter 6 we will be doing, I think, before Chapter 5 because of Dr. Farley's lab. Let's just say that Chapter 6 will be the next chapter I'll be filming next week. Okay, so look at that Castle Hayne limestone. Okay, so we have it naturally outcropping just west of Wilmington in the little towns of Castle Hayne, which is kind of out beyond Laney High School and real close to the other campus of Cape Fear Community College. I forget what the name of that campus is. And then, of course, Rocky Point as well. Okay, so think about this. Limestones are marine rocks. They form under water, salt water. All right, guys. So there you see where sea level is today in my drawing. All right, so let me ask you something. Where must sea level have been? What must have been true about its level 35 to 50 million years ago? I'll give you a second to think about that. You have an answer? Sea level was higher. How do we know that? Because we find it a decent distance west of where sea level is today, and we find this really thick deposit of limestone, and we know that it was deposited when sea level was higher. Now, in my drawing, and in reality, 35 to 50 million years ago, did sea level ever encroach on the land high enough to make it to Raleigh? You got an answer? The answer is no. How do we know that? Because we don't have Castle Hayne limestone in Raleigh. All right, moving on. We'll just scoot right here. Yes, I'm going to be sitting because, again, I'm a little tired already. All right, cross-cutting relationships. This is going to involve igneous intrusions and faults, things that cut across or through other rock layers. Okay, so just by the way, remember that strata is just referring to more than one layer of rock, a bunch of rock layers together. So igneous intrusions and faults that cut across or through strata, that intrusion or fault must be younger than the strata that it has either cut across or displaced. Okay, and hopefully this will make sense as we look at these two drawings. Let's start with the one on the left. A reminder there in blue, one is always oldest. On the left there, we have sediments on top, limestone below that, sandstone below that, shale below that, and then we have this basalt dike. So we're going back to one of our, I guess, chapter 2. This basalt dike cutting through those layers, cutting across those layers, all right? Now, so what can we say about the relative age dates, putting them in sequential order? What must be the oldest? The shale, it's on the bottom. Okay, so we're also using superposition here. The sandstone's younger than that, limestone younger than that, okay? But then the next youngest is the basalt. So the basalt must be younger than the shale, sandstone, and limestone it cuts across, as in those layers were already there before the igneous dike cut through there. And then the sediments got deposited on top sometime later. So they are the youngest, and they are number 5. All right, scooting over just a tiny bit. Now we have a drawing there to the right where we have some offset. So those of you that have had earth science class, my hope is that you remember that this is a normal fault. Okay, the hanging wall is on the left. It's the block of rock above the sloping fault plane, and it has moved down. That's a normal fault. What do we see? We see here layers of sandstone, limestone, shale, and then we can see conglomerate on one side. Where is it on the other side? I think it's covered up with sediments on this is on the side of the road, a road cut. And then we see a fault that not only has cut through these rock layers, but displaced them. Okay, so what is the oldest thing on this drawing? The conglomerate, it's on the bottom. Shale is younger, limestone's younger, sandstone's younger than that. What's the youngest thing of all on this drawing? The fault. Okay, the layers of conglomerate, shale, limestone, and sandstone were already there before that fault occurred and had movement of the hanging wall dropping down. All right, we're going to scoot over. Maybe we can just go like this. Okay, so we're still in our geologic principles here. Inclusions. Any piece of rock that has become included in another rock or body of sediment must be older than the rock or sediment into which it has become incorporated. So our drawing there says it all. We have sediments on top, a layer of sandstone below that, and a big granite body below that. Now, those orange polygons are granite inclusions. So what this is telling us is if we saw this on the side of the road on a geology field trip, we would walk up, we park somewhere and hopefully there's the road is wide and it's safe to be hanging out on the side of the road here. And we go up and look at that sandstone and we see big pieces of granite in the sandstone. That right there is proof that the granite must be older than the sandstone. Not only is it below the sandstone, and of course it could be an old intrusion and the young stuff it intruded into eroded away and then the sandstone was deposited later, but that granite was there before the sandstone was. And as those sand grains are being deposited, there were pieces of granite being kind of plucked up and incorporated into the sandstone. I'm going to point out that we don't have any contact metamorphism here. Okay, you don't see any little X's on this diagram. We're going to see some X's when we get to baked contacts. Bottom line here, the granite is older than the sandstone. All right, moving over. All right, how are we doing on time? Okay. Principle of fossil succession. Fossil assemblages succeed one another through time in a regular and determinable order. There's not really a drawing that I need to do for this. We're just going to say that clever scientists have been researching fossils and doing field work and digging them up and studying them and cataloging them for many, many decades. And we know which species of trilobites, for example, came first, and we know when they went extinct and when new species came along, and so forth. All right, baked contacts is going to have a drawing here. Okay, this is referring to contact metamorphism. Okay, so this might look similar to something we saw in an earlier video lesson. Okay, rock that has been metamorphosed as a result of an igneous intrusion. Oh, I knew that was going to happen. Okay. Yeah, if you don't move around the whole room, then the light goes out and I have to walk all the way back to where the door is to get it to come back on. I'm in this room by myself, which is fine because then I can take my mask off and jabber away all I want to. All right, back to baked contacts. So what this is telling us is that a zone of contact metamorphism will let us know that that rock that has been baked or metamorphosed must be older than the intrusion. So let's look at our drawing here. What do we see on the side of the road? We see sandstone on top and a limestone below that and a bunch of shale below that. And then we see this granite punching into the shale. And we go up close and look at it and we see that the shale close to the granite has been metamorphosed. And maybe it's garnet mica schist, for example, instead of shale. Okay, so the X's there are zone of contact metamorphism. That's always how I show a zone of contact metamorphism, are with these X's. Clearly, the shale and the limestone were there before that magma body intruded, and we know that because they were permanently metamorphosed as a result of that intrusion. We don't know about the sandstone. The sandstone could be younger or it could be older. Moving on to another board. Just a little bit left to do. I think that some of our upcoming chapters that we're going to be filming for are going to be longer than the ones we've done so far. Okay, that's all right. That's just work for me. Hopefully it's not too bad for you guys. Okay, oh no, I'm going to have to move around, right, because of we're going to try to get rid of the light glare if we can. Okay, here we go. So just some examples here, okay? Here we're looking at a buried lava flow versus an igneous sill. Remember that an igneous sill is an intrusion below ground, tabular in nature. It's basalt. It's very much like the igneous dike, except that it is parallel to rock layers. And what's a lava flow? A lava flow is exactly what it sounds like. If you go to YouTube and you type in flowing lava, you're going to see video from, I'm sure lots of videos there from Kilauea of lava flows, both in action and after they have cooled. We'll start there at the top with the buried lava flow. This is what we see. Okay, we see limestone on top, and then we see basalt below that, and below the basalt is a sandstone. And the sandstone, at the top of the sandstone where it touches the basalt, we have a zone of contact metamorphism, as in that looks more like quartzite. Now notice that the limestone above is not metamorphosed. So the basalt did not sneak in between the sandstone and the limestone. The sandstone was the top layer. The basalt flow came on top of that, baked a little bit of the sandstone below, and then cooled, and then later on the sea level rose and the limestone was deposited. And then the blue circles there are basalt inclusions. So we can use a lot of these different principles all together on some of these diagrams. So you also have inclusions from the basalt into the limestone as further proof that the basalt is older than the limestone. And of course the absence of any contact metamorphism on the limestone says the limestone is the youngest. Now on the bottom is the igneous sill. You have basically, where you have sandstone on the bottom, you have layers of shale, and then you have this basalt sill running horizontal that is parallel to shale layers, kind of cutting through the shale layers. Notice the X's. You have contact metamorphism on the shale below the basalt and the shale above the basalt. This tells us that both shale layers were there already, and the basalt, it was not running across the top of the ground. This was an intrusion, and it squeezed in between the two shale layers. Okay, so that's a buried lava flow versus an intrusion, what they might look like in our homework. All right, a little bit more. Nope. How can we get rid of the, there we go. Shouldn't run into the table. Okay, I think that'll get rid of the light glare enough. A little more on radiometric dating. Igneous rocks are the most perfect specimens for radiometric dating. And the date that you get tells you when that lava or magma cooled and became rock. Metamorphic rocks can be tricky. I don't know if we'll go into any detail on that or not this semester. There's a little bit in, I think it might actually be chapter 5, a little bit more about metamorphic rocks. I don't know that we'll have time to cover it. It'd be okay. Know this about sedimentary rocks. Most sedimentary rocks cannot be radiometrically dated. Let's say it's a sandstone, okay? And you got quartz sand in there. that used to be a granite. So maybe there's some uranium in the quartz. I mean, could you get an age date from the uranium on that quartz sand grain? You could, but that's not telling you the age of the sedimentary rock. It's only telling you what would be the date for the granite that it came from. And that could be way many millions of years off. So we cannot use radiometric dating for sedimentary rocks. We mainly use indirect methods, and that's actually kind of fun, and we will talk about that in class eventually, one of these chapters. That exception is something I do want you to know for the exam. Actually, everything here is exam and or quiz worthy, otherwise I wouldn't be putting it on the board and filming it. But this is definitely an exam question here. There is one exception. There's a mineral called glauconite. It's really cool. It's a green mineral that only forms in certain marine muds and sands. Not all marine muds and sands are going to have it, but some will. If it's reducing, meaning it's not oxidizing. So instead of going up in charge, it's going down in charge. Anyway, so if you are studying rock strata and you have marine sands and muds, if you're lucky enough to find glauconite there, you can get a radiometric age date for that sedimentary rock. One last thing for this video lesson. The Vostok Ice Core, Antarctica. We can go back 800,000 years of reliable data. We cannot go back any further. That's okay, we don't really need to. That tells us a lot, and we even have the last polarity flip of the sun in there at 700,000 years. We're looking at oxygen isotopes, a ratio of O18 to O16. O16 is one isotope of oxygen, and what I kind of consider just normal oxygen, as in 8 protons and 8 neutrons. But remember isotopes, so O18 still has 8 protons, it has to, it's oxygen, but it has 10 neutrons. Remember, there can be a different number of neutrons, therefore a different weight. So looking at the ratio of O18 to O16, is it higher or lower? The isotope ratio shows us levels of carbon dioxide and temperature in the air pockets that are trapped in the ice and fell with the ice at the time that snow fell. So the Vostok Ice Core tells us a lot about climate change, and yes indeed, things are very different now ever since the beginning of the Industrial Revolution. That'll do it for this lesson on Chapter 4. Peace out.